You are given some boxes that are labeled from 1 to n. So this is box number 1, this is box number n. And each box can have several number of balls inside it. So suppose this box has 5 balls, this box has 7 balls, this box has 9 balls, this box has 0 balls, and so on. Apart from that, there is also a special box called the community box that has a certain number of balls, like let's say it has 20 balls. Then the rules of the game are n person are n people are sitting on a circle with this person count the leader of the circle. Basically, this circle has an orientation, it needs to start from here, and this person will start the game, and they can either take one ball either from their own box, which is the box number 3. They can take one ball from here, or they can take one ball from the community box. It is their choice completely. Then the game moves on to the second person, which is this 7. So this person can either take one ball from their own box or one ball from the community box. And then the game continues around the circle until it reaches 5, and then this game wraps around and then reaches this person. So this person will again make the same choice, that they can either select a ball from their own box or a ball from their community box. Now notice that ball person number 4 does not have any balls inside their own box. So of course, whenever it is person 4's turn, they always have to select the community box to select a ball out of it. Now once the game is going around in a circle, this is what the first round will look like, this is what the second round will look like, this is what the third round will look like, and so on. So if it so happens that on the fourth round this game is continuing, but this person is not able to select any balls. Why? Because their own box is empty and the community box is also empty. Then we say that these set of persons will not be able to finish this game. Why? Because there could be other balls remaining inside some person's boxes. So you have to figure out whether it is possible to take all the balls, including the community box and including all the individual persons boxes, by following this rule. That is, if you go in this fashion, will you be able to take all the balls from all the boxes? So once the game finishes, and suppose the last person of the round was the one to take the last ball, then you have achieved a possible configuration, otherwise that configuration is invalid. So how do you solve this problem? So this is where in this video we will talk about some greedy ideas to solve this problem, while also seeing some tricks that help you avoid off by one errors that usually appears in these kind of problems. So let's go back to the problem again and notice that the special box that you have, the community box, from your gut feeling, would you want to take a ball from the community box first, or would you want to take a ball from your own box? Do you want to take a ball from box I or from the community box? Now remember that the goal of this game is to finish all the balls for each person. You don't have to act selfish. Everyone has to finish their balls, right? And the balls at box I, they can only be touched by you, right? So this only belongs to you. Therefore, if you start taking things from the community box, then it is possible that if the game is going on for 5 rounds, or let's say 3 rounds, then even if you had 3 balls in your own box, like let's say you have 3 balls and there were 3 balls available in the community center, then if two persons are playing a game, then if both of them try to take balls from the community center first, then you will exhaust all of these balls in the community center, and then the game will end and you will not be able to clear out your own balls, because these can only be touched by you. So you have to clear them out first. Otherwise, once you are out of the game, nobody can delete these balls from these boxes. So that is why the greedy idea makes sense, that first you select the balls from box I, right? You always choose box I, always choose your own box. But yes, if it is if you are running out of balls, then in that case you can go to the community box. Else, if you run out of balls, you can use the community box. You can use the community box. So now the greedy idea is clear, and why this greedy is correct, it's due to the reasons that we discussed, that if you clear out the community balls first, you are doing two things. One is, not only are you making things a bit more difficult for the balls at box number I, which is your own box, to be cleared, you are making it very difficult because nobody else is going to touch it. And the second thing is, if you are touching the community box first, then you are making it very difficult for other people who have very minimal balls in their boxes. So suppose this person has 0 balls or 1 balls and so on, you are making it very difficult for this person to get all their deficit from this box. So that's why you have to clear your own balls first in a greedy manner, and then only then use the community box. So how do we figure out whether the answer exists, right? So we know that this is the optimal strategy, but how do you solve this? Because you will not be able to simulate the entire thing, because the total amount of balls in all these boxes can be up to, like, let's say 10 to the power 18 or something. So how do you come up with a good strategy to figure out whether it is possible for these persons to finish out the game? So that is where Euclid's division lemma comes in. And let's go back to this. So this is the community box. Everyone can use it. And then you have boxes for each person. So each person has their individual locker, you can say. This is 1, this is 2, 3, 4, and 5. Now, what is the total number of rounds you will play? So the total number of rounds that will happen, you know that you have to clear out all the balls, right? So basically, how many total balls will be utilized? So that will simply be summation of AI. Let's call this as S. By the way, this is A0. This is the first element. We are considering this as A0. This is the community box, and these are the other elements. So this S is the total number of balls to be consumed by all the players. Now, once you have this S, basically the sum of all the integers, from Euclid's division lemma, so this is actually a very important concept. From Euclid's division lemma, you know that you can write any number S as equal to n into quotient plus remainder, because right now we only have two numbers to deal with. We know the total number of balls that has to be consumed and total number of persons that exist, which is equal to r, which is equal to n. So this is what Euclid's division lemma says. S is equal to n into q plus r. This will make it very easy for you to reason about things where there is some remainder. So, and the lemma says that if you have this expression where S and n are known, it is possible to figure out this q, which is the quotient, and r, which is the remainder. And the formula is r is equal to S modulo n, and q is equal to S upon n and floor of this. Now, a lot of people get confused, like how come modulo and division suddenly appears in these kind of problems, but this actually originates from these Euclid's division lemma. So looking at this, so instead of looking at S, which is the left hand side, why don't you look at the right hand side? So right hand side means the total number of balls that you have to consume is equal to n into q plus r. Now, if you visualize all the people as sitting on a circle, then what does n into q represent? N into q. So, what does n represent? It means that there are n people on this circle, right? So, this is the first person, second person, third person, fourth person, fifth person, and let's say n is equal to 5. So, n into q means walking q times around this circle. So, one time you walk, you encounter n different persons, and then you walk another time, you will have covered n. So, if you do this walk q times, you will get this number n into q. So, this q is nothing but number of full walks on the circle. Number of full walks. But what does this R signify on this circle? So you can see that you have performed Q full walks on this circle. And then on the last walk, you will start your journey from here. And then you will be only able to walk a total of Q steps. So this is what the game pattern looks like. This means that for n people to play this game, the game will continue for Q rounds, where each round you walk on a circle completely, and in the last round you will not be able to complete your walk. So you start from here and then you only cover the first R people. This means that had the last round not been there, then every person would have picked up the same amount of balls, right? So let's see how to incorporate this R to make sure that this condition is specified for a this condition is satisfied for a given configuration of balls and boxes. So we'll start out with this division lemma only, and this time, so this is the division lemma, and right now we know how to compute R and Q, so I'm going to remove the formulas for those. Okay. Now let's consider person 1. In how many rounds will it participate? We know that you are performing Q walk on the circle and then a partial walk on the circle. So one thing is for sure, each person needs Q balls to participate in those Q rounds. So that part is for sure. Then, since you are given the configuration, you are given the initial ordering of the people. So this is person 1 is standing over here, person 2 is standing over here, person 3 is standing over here, person 4 is standing over here, and person 5 is standing over here. Then you can take the first R people, suppose R is equal to 4, and then you can go to those locations and then you can increment by 1, because these R people will participate in the last round, right? So doesn't mean that first 4 people, right? It means first 4 people on this circle. So P1, P2, P3 and P4. So that's why it could be this, like these 4 people participating in the last round. So now we know how many balls each person needs, but how much do they already have? That part we need to figure out. So you can see that once you have computed this quantity, right, which is q plus something, q plus either 0 or 1, depending upon whether this person participates in the last round or not, then what is the deficit? What is the deficit for each person? So assume that this community box is not present. Why? Because we said that first we'll try to complete our boxes first, and only then we will use community box if it is really needed. Then for the ith person, the deficit will be equal to, it has a of I balls, right? And it needs, suppose you define this as need of I is equal to q plus 0 or 1, that this part you will decide based upon whether this person lies in the first r people of the circle or not. So deficit of I would be nothing but, so how much extra balls does this person need? That will be nothing but, it needs this amount of balls, need I, minus it has this a of I amount of balls. So this person needs this much balls, right? But if this deficit is less than 0, it means that this person has extra balls, and it will not be possible to, clear out all the balls for this person I. Why? Because this game definitely has to end after q plus 1 rounds. And if your total balls is greater than q plus 1, then there is no way that you will be able to clear out the extra balls that you have. So if deficit of I is less than 0, then you know that the answer is not possible. So now you can assume that all deficit of I is greater than 0. Then if you look at this, if you look at this quantity, sum of deficit of I, this means that this is the total amount of balls that is needed by each person to complete their full q plus 1 rounds. Then where would you get these amount of balls from? This should come from this, the community box. And in fact, since you know that community box also has to become empty after the game, then this expression should hold. That is, this deficit of I should be equal to a of 0. So if this condition, and this condition is satisfied, then you can see that it will always be possible to finish the game if you follow the strategy that we discussed. That is, take a ball from your own box and only use the community box once you are out of balls. And in this manner, if this condition is satisfied, then you know that you have a deficit of either 0 or some positive number. Then you will be able to empty out your box in those q rounds because you have a deficit. And in the last couple of rounds, you can use the community box to get the remaining amount. And if this condition is also being satisfied, then it means that the answer is yes, it is possible to devise a strategy in which this game can end. So this is one problem that we saw of how to use greedy algorithm and how to use Euclid's division lemma to avoid off by 1 error. Because if you did not know about this concept of Q and this concept of R, it becomes very tricky to solve this problem. You might end up making a lot of off by 1 errors and then confusing yourself of what is, how does modulo come into picture in these kind of problems, how does s by n come into picture in these kind of problems. So this is the easy version of the problem. Now in the hard version of this problem, I want you to find out. So this time I had given you this, the configuration of the boxes and I had also given you the configuration of the people that are sitting on the circle. So I said that this is the permutation that is arranged on a circle, and tell me, is this permutation a valid permutation? It means that can this permutation, can this set of people that are sitting in the circle, can they go in a cyclic order and finish all the balls in all the boxes, right? So you came up with a strategy for that. Now let me ask a more general question. This time you are given the set of boxes, including the first box, which will be the community box, and then you want to find out, this time you are not given the configuration of people. Okay, you are just given some balls and some boxes. Let's say it has 5 and 2 and 1 and 0, 22, 19, and so on. This is box number 1, box number 2, box number 3, box number 4, box number 5, box number 6, and this is the community box, which is labeled as box number 0. Now I want you to find out, in how many ways can you arrange n people on a circle, right? So how many ways you can arrange 6 people on a circle so that these 6 people will be able to finish the game, and after the game every box should be empty, including the community box. So how do you solve this problem? Again, you can use the same strategy from before. You know that permutation is not given to you, but you know S, which is the sum of balls in all the boxes, and this S is nothing but N into Q plus R. So even though you don't know the ordering of the people in this circle, you know that no matter what ordering you choose, everyone has to compulsorily participate in Q rounds. That is for sure. So let's worry about this last round later, right? So every person has to participate in Q rounds, and the first R person will participate extra in the last round. So then this person, so for this box I, what is the deficit? So this person has to participate in Q rounds, right? So the deficit would be max of 0 comma, it needs Q balls, right? So you define it as Q minus A of I. This is the deficit. Why I'm taking max? Because this deficit can now be uh, positive, right? Sorry, this deficit can be negative, meaning this has some extra balls. But uh, now the condition will become that this deficit, okay, so this person needs this deficit, okay, and this person will also have a leftover, because if you are counting deficit, and previously we had exact one-to-one mapping, that is deficit was known explicitly because deficit was defined as need of I minus A of I, but this time we don't know need of I, but we know that need of I will be at least Q and then some extra like either 0 or 1. But since we don't know that, let's only consider the game for the first Q rounds. Okay, so that's why we have defined deficit as max of 0 comma Q minus AI. So what will be the leftover? So how many balls does this person have extra? So you can see that it will be simply max of 0 comma AI minus Q, right? Because why is this the leftover? Because it has total AI balls and it is only participating in Q rounds. So this is the leftover balls that this person has. This means that, what can you comment about this leftover? We saw that this leftover balls should either be 0 or 1. It cannot have more than one extra balls, right, after participating in Q rounds. So the first condition should, this condition should definitely be satisfied for any answer to exist. That is, leftover of I should be less than or equal to 1. It cannot be greater than 1, because if it is greater than 1, it means that this box has so many balls that it would take more than Q plus 1 rounds to clear out all the balls. Okay, so this is about the leftover. What about the deficit? So each person will have a deficit, and this deficit only corresponds to playing for the Q round, right? So what about the sum of deficits, right? If you look at this quantity, sum of deficits. So this sum of deficit, should it be equal to this, to the number of balls in the community box or not? Because previously we had this expression, right, that the sum of deficit should be covered by the community box. So you will realize that this time it will not be an equality, because this deficit you have only counted for the Q rounds. What about the case where the last round some R people will participate, and community box might hold additional balls for those R people? So the only thing that you can safely say, that this deficit will be less than or equal to A of 0, which is the community box that is available. So we have two conditions that we have identified. One is that sum of deficit should be less than or equal to 0, so that this condition ensures that each people participates in at least Q rounds, right? This condition ensures. And then, and the leftover of I, leftover for each I should be less than or equal to 1. So we have identified these two as the necessary conditions for a permutation to be valid. And in fact, for this, you don't even take the permutation into picture. Like, if this condition is not satisfied, then no permutation can exist, because no matter what you create, some boxes will have some extra balls. But one thing that might not be obvious is that this is also the sufficient condition. Why is it sufficient? Because this condition, right, this sum of deficit less than a less than or equal to the community box, this ensures that every person has enough ammunition to participate in Q rounds. This means that after Q rounds, each person will either have one ball or zero ball. So let's say you have 1 and 0 and 1 and 0 and 0 and 1 and so on. But then you might get confused and think, okay, why is this condition actually sufficient? Because what if all of these person have one ball, one balls each, suppose this one, and then community box also has some extra balls, like let's say suppose it has 5 balls, because we only added less than or equal to condition, right? So can a condition not arise where you have one balls in each of these person, okay, and community ball has one extra ball, or like let's say two extra ball? Can this situation not arise? So the answer is that it will not arise, because again, it all boils down to Euclid's division lemma. So it says that S can be expressed as n into q plus r. This means that if every person has participated in q rounds, this means that the total leftover is equal to S into S minus n into q. This is the total leftover, and this is equal to r. And Euclid's division lemma says that r should be strictly less than q. This means that if this situation were to arise, then every person was capable of participating in q plus 1 rounds, right? So instead of making them participate for q rounds, you should have done it for q plus 1 round. So this Euclid's division lemma, it guarantees that this r will be strictly less than q. This means that once you have subtracted n into q from the total sum, then the total leftover is guaranteed to be less than q. This means that this condition will never arise if these two conditions are met. So now we have a necessary and sufficient condition for any permutation to hold. So let's see how to construct the permutation, or in fact how to figure out how many unique permutations are there that can satisfy this criteria. So you can see that if this condition is satisfied, this deficit condition, then every person will be able to participate for Q rounds. No doubt in that, because they can either take some balls from their box, or if it is empty, they can use the community box while being tension free that the balls in the community box will not run out. Everyone will have their fair share in the community box. So the only thing that matters is the leftover, like how much leftover each person has, and that is also fixed because here we are saying that leftover is less than or equal to I, but we computed the leftover via this formula, so this is fixed. So this means that there is a binary string containing zeros and ones. So suppose this is a 0, this is a 1, this is a 0, 1, 1 and 0. And community box can also contain some 0, like some ones, like let's say it contains 3 ones. And let me extend the box by some more. Then what can you say about the configuration of the people on the circle? So for the first Q rounds, it doesn't matter who is sitting where, but the last round will uniquely determine who is sitting where. So every person who has a 1 associated with the leftover, they have to necessarily participate in the last round. So this means that you count all the ones, right? And you, like, let's say you label them as x. X is equal to leftover. X is equal to count of leftover of I equals 1. So you count all the persons who have an extra ball remaining. So these person will have to compulsorily participate in the last round so that they can consume their ball. So, and then you define, so if X is the uh, total number of elements where the person has to participate in the last round. So one thing is guaranteed, that if the total number of elements in this arc is equal to R, then these person will have to sit inside this arc itself. And if you define Y as the remainder, basically Y will be all the peoples who do not have a 1 at that position. So Y is nothing but n minus x. Now notice that in this set of R people, the position of x people is fixed because they have to be present in this circle. So what is remaining? So the remaining amount that you have to get should be equal to R minus x. You have to collect these people who have been assigned 0, and you have to tell them to participate in the last round by using the community box. But you can select these people from the ones that have been assigned 0. So how do you select that? So you can do R minus x. You have to choose how many people? You have to choose R minus x people from this set, right? So the total number of ways would be Y choose R minus x. And then once you have chosen R minus x people and x people have already been fixed, then you can permute them amongst themselves, right? So that you can do the permutation in x factorial way, sorry, R factorial way. And then for the remaining people in this branch, you can also permute them in n minus R factorial. So overall the formula becomes, writing it once again, among the people who have been assigned 0, you select some people who will land in the first arc of the circle. And how many people do you need? You have already x people fixed that will participate necessarily. So the remainder of people that you need is equal to R minus x, and this R is nothing but this R that was appearing over here for Euclid's division lemma. And then once you have arranged for R people by taking x from here and then picking the remaining from the other parts of this array, then you permute them amongst themselves in R factorial ways. And for the remainder of people, you can also permute them in n minus r factorial ways. So this is the total number of permutations that can satisfy the constraint and still make sure that all the boxes are empty after the game has finished. So this was one application of a problem where you could apply greedy algorithms and Euclid's division lemma to simplify things.